Hello again, Calculus 2 students. We are continuing with 8.1. We're in the final stretch. We're talking about area. We did dx and dy last time, and now we're going to do things a bit more broadly. We're going to talk about just shapes and creating area with shapes, and that's going to be a transition into doing volume. So the warm-up I would have you do in class is have you try to remember what you know about similar triangles. So feel free to pause and try to think about that for a minute, and then start the video again. So let's try to draw a similar triangle, and then try to draw a triangle and then a similar one inside that one. So here's some ideas. Well, first off, similar means you have the exact same proportions, basically, the same angles. I didn't do a very good job because that looks like a right angle. These are supposed to be the same, and then the top is supposed to be the same. So I did a terrible job, but one easy way to do it is when you have a right triangle and you do this. So those angles are the same, those are both right, and then we're sharing this angle. So that's an easy way to have a similar triangle inside another. And we're going to use this idea to do some problems. Okay, so we're going to draw an isosceles triangle with width 10, so very wide, height half that, 10 I can draw. You will, by the end of this unit, you will realize that it's good that I don't teach Calculus 3, because I can't draw. And I want to slice this up. I want to add a bunch of little rectangles. So this slice, think of that as a very, very thin rectangle. What's the width? Well, okay, we're going to call this 10. And this is 5. This width we're going to call W. The height would be H, right, for height, but it's one of those little tiny rectangles. These infinite things we're going to add up, so we're going to write DH. Okay, and this integral would be WDH, because that's rectangles are length times width. I know it's a triangle, but the slices are rectangles. And so the height goes from 0 to 5. This right here is important. Okay, the idea of coming up with that integral generally, it doesn't have an x-axis or a y-axis, it's just the idea of integration by adding up these rectangles. Make sure that you understand that concept, because we're going to use that a lot. Okay, how do I convert W to H? Well, I don't have an equation, right, or a nice xy graph, but I do have similar triangles. So if you look at this big graph here, or it's not graph, but triangle, this little one is similar to the big one. Or if you do the right triangles, you can see that as well. So that means that, think of H, so you have DH, but H is the height at which you get that DH. Right? So W compares to 10, because W is for the little triangle, and 10 for the big one. That's the same comparison as, if that's H, the stuff above where the little triangle is, that would be 5 minus H. Make sure you're okay with that as well. So 5 minus H would compare to the big height of 5. That 5 minus H concept is pretty strange and an important one, so make sure you also understand that idea. These two things, height, that's how far up you are, but these two things should add to 5, so that's why I got that other number. Okay, well, I can solve that for W. So multiply the 10 over, that becomes a 2, and I have 10 minus 2H. Okay, so I should integrate this, and I'll go ahead and do it out. And then it says, how can I check my answer here? Okay, so I'm going to get 10h minus h squared, because it's 2h squared over 2. 2's cancel. We got to write those out. Those go away. And then plug in 0 and 5. So I get 50 minus 25, and 0 minus 0. So I get 25. How do I know that's the right answer? Because the formula for area of a triangle is 1/2 BH, and B was 10, and height was 5. So half of 50 is 25. That answer makes sense. Okay, so it seems kind of a waste of time because we already knew the answer, but we're going to generalize these concepts to formulas that you don't know yet, so that's why we're doing this. Okay, so we did our triangle. We got the area formula to work how we wanted using integration. Now we're going to do cones. All right. Okay, so now I want to talk about cones. We're going to skip the Plickers question. It was just about what is the best way to slice a cone, and I will show you that. All right, so let me draw the slices. So we have a very wide cone, same idea. Here's the cone, and height 5. This is the side view of a cone, but it's all the way around. Okay, so picture that as a cone. Again, I can't draw. We're going to slice across so that each little slice makes a disc. Imagine if you've ever had, when you were a kid, if you had those little toys that had a yellow pillar in the middle and you put rings around it, and you didn't have infinitely many slices, but those little rings together made a cone. That's the same idea. It's a stack of rings on top of each other. Okay, so the shapes make rings, but we're going to call them circular discs. Okay, so if you did this in Calc 1, you call it the disc method. That's what we're talking about. We make circular discs. What's the area of each slice? Well, it's pi r squared for the circle, but you also have a little bit of height, right? So each of these rings has a radius r. So that's what I mean by r, and they're at a certain height. We put dh up here, so we'll put it up there. So pi r squared dh. And I'm just going to integrate that. That's an area times a height, so that's going to make a volume, which makes sense because cone is a 3D shape, right? And the height goes from 0 to 5. So this is a little different than the previous problem. But the side view is still the same. If you think about this whole thing, the diameter was 10, so the radius is 5 for the, let me draw the shape again. There's 5 here, but this was also 5. And then here, that little r is going to compare with that triangle is going to have 5 minus h up top and not h here. So that's the same picture. So it's just like before, except rather than doing w and 10, r over 5 compares to 5 minus h over 5. Okay, so let's go ahead and solve that for r. The 5's cancel, and r is equal to 5 minus h. Okay, I want r squared, so this is going to be from 0 to 5. Pi 5 minus h squared dh. I could FOIL this, but it's quicker if I just do a small w substitution. dw would be negative dh. So I get 5 to 0, because remember I have to change my limits as well. Pi w squared dw, and then I'll flip that around. 0 to 5, pi w squared dw. Then you'll get pi w cubed over 3, plug in 0, plug in 5, and you should get 125 pi over 3. You probably, maybe, learned the cone volume formula before. That was 1/3 pi r cubed, and that's what we did, right? We had the 3 on bottom, we had the pi, and then the cube of 5 is 125. Okay, so let's go back to 2 dimensions. So I don't have a ton of space here, but we'll try this here. I want to use horizontal slices to find the area of a semicircle. So now we're going to do something different. We're not going to use similar triangles this time. We're going to use a different trick. Here's a semicircle. The radius is 7, so that's 7, that's 7. And here's the key trick. When you make a slice, so I want to slice horizontally, there's another 7. So I'm at this height, and I've got this radius here. This is also 7 because it is the radius again, right? It goes from the center of the whole circle, which is the bottom of the semicircle, to the edge, so that's 7. Okay, and now I can use the Pythagorean theorem here. So r squared plus h squared equals 49, 7 squared. And the integral, let's back up for a second. The integral that I'm trying to do is, I'm in 2 dimensions, so I'm really, at each slice is 2r, or before we use w, but I care about the radius now. dh, right, dh is the thickness here. And I'm going from 0 to 7. And I just figured out how to solve for r up here. So r is 49 minus h squared, square root. It's a length, so I want the positive. So my integral is this. I am not going to do this by hand because I don't want to, because we passed our gateway, but you should notice this is a trig sub. I would have to do this. The reason I'm making this point is because trig sub was not designed to torture college sophomores. it was, and freshmen and seniors and juniors. It is there because it needs to be, because there are physical applications that came first, and we care about these kinds of integrals, and you'll see another one later. And then people wanted to know how to do these integrals. That's why trig sub exists, because it actually is useful. Anyway, the answer should be, well, you can put the symbol from alpha, you can do the trig sub out, or you can think about how this should work. A circle with radius 7 would have pi r squared, so it'd be pi times 49, but this is a semicircle, it should have half the area. So that should be the answer. And I believe if you work this out, that's what you'll get. So if you want to practice for your final, that would be a great thing to do, or if you haven't passed the gateway yet. All right, so that was back to 2 dimensions. We're going to use that exact same picture. So let me actually just keep the picture here for you guys. We're going to extend that to a hemisphere. So we're going to keep all of that. We're not going to keep the same integral, but we want to do a...
Here's what I found.
Google apparently thought I said, hey, Google, and wanted to look that up for me. Sorry for the distraction there, guys. All right, so... sorry, that's what train of thought. We're going to use the previous problem. We're going to do the exact same picture, but it's a hemisphere of radius 7. So I'm going to check my answer again. So this is the side view, but imagine that that's not just a flat circle, it's a dome, right? It's a hemisphere. And so same picture, same Pythagorean theorem, but my integral, each slices are, like before, they are circular discs, and that's going to be a most common slice for 3D objects. If we cut that cut there is going to be a ring, right? Filled in. So I want pi r squared dh from 0 to 7. This looks like the problem for cones, except my r and my h relate differently. I have this formula up here. So now r squared is just 49 minus h squared, and I don't have to do any trig sub, which is nice. So I'm just going to change r squared to 49 minus h squared. I'll put the pi on the outside. This is dh. So 49h minus h cubed over 3, 0 to 7, all times pi. And if you plug in, I don't want to do 49 times 7 in my head, so we'll call that 7 cubed minus 7 cubed over 3, and then minus 0. All times pi. So that is 2/3. Ignore the scratches over here. That's 2/3 times 7 cubed times pi. Okay, if you learned volume of a sphere before, it was 4/3 pi r cubed. Why do we have 2/3? Well, because we have a hemisphere. So that would be the final number, whatever that number is. All right, now we're going to do one that's a little bit off the wall and has, there's not any previous shape. We're going to actually do the volume of the Great Pyramid of Egypt. Okay, so that shape is a square pyramid, so you have triangles on the side, but this is the side, but the bottom is a square, right? 755 by 755. So when I make a cut across the middle of it, this is not rings stacked on each other to make a cone. This is squares stacked on each other to make a pyramid, right? So the slice is a square. So here's a height and here's a side length. And here's my, sorry, that's not very straight across, but there's my dh. So my integral is going to go from 0 to 410, because that's the height. Each slice has s squared for the area, and dh for the width, or as height of that slice, this part, the thickness. Okay, I need to convert s to h, and we're back to similar triangles again. So think of this triangle here, if I could draw straight, and then this big one. So the big height is 410, the little height is 755. So that tells you that s over 755 compares to 410 minus h, because that's the top here, over 410. So if I solve for s, I want to integrate this crazy thing. 755 over 410, 410 minus h, all of that squared dh. And we can use a calculator, we can use whatever we need to for that, and we'll go ahead and get that number just That number is approximately 78 million cubic feet. It's pretty big. All right, so that is our intro to doing volumes. We're generalizing this idea of slicing, going from area going to volume. There are some general abstract concepts about setting up these integrals here. It's always set up the integral and then convert the variable, which is also what we did with the x's and y's. If you don't understand that, you need to talk to me ASAP because that's the key principle. All right, next time we'll go to 8.2.